So this time what we're going to do is we're going to do a video which is not necessarily a tutorial or an exercise on how to compute anything in math. I'm going to probably compute some stuff, but what I'm basically going to use is my knowledge about mathematics to talk about special interest topics or things that I like to talk about. The first series that we're going to run is a series on a bunch of different numbers. So one of my favorite numbers of all time is the golden ratio, phi, or the divine proportion, or the extreme and mean ratio, or the mean ratio. Actually, that box was supposed to be on everything there. So we want to talk about the golden ratio today, or the divine proportion, or the extreme and mean ratio. I fixed it. So what is this? Basically, this comes from geometry. A lot of the first weird, strange numbers that you'll see that in this series come from geometric considerations. So in this case, the one I like the best is from Euclid's Elements, 13 Elements. He describes this as the extreme and mean ratio. What that is I take, oh, he tried to be curvilinear. No, I want rectilinear. So I want a straight line. So I have a line segment. Let's call it AB. So once I have a line segment, any line segment of any length, yes, I cooked it up. I pre-put my dots there so it'll work out so I can draw this for you. But in another video, I'll actually show you how to construct the extreme and mean ratio. In this one, I'm just going to pretend I already did it, and we're going to use it, and I'll show you what happens with it. So I take a line segment, which is finite. It's got two endpoints, A and B. What we want to do is cut it in a single cut. Magically, there it is, roughly. That cut says that if we can cut this, we're going to take the whole ratio, and then now this is ratios and how we denote this, so there's a bunch of notation sort of that we're going to use for Euclidean geometry, but I'll just put them in there, and then I'll use the regular algebra that we've been using in the other videos, x and y and those types of things, and we'll solve for x and find out what the golden ratio is, phi, the golden ratio. So first of all, in Euclid's 13 Elements, what he says is the extreme and mean ratio is taking any finite line segment, cutting it with one cut, such that that is a magic cut where I take the whole segment. So let's call this point F. I think in the construction I need a bunch of different points in the actual geometric construction, so the last one I use is F. So I cut it at some point F. What is that? Now I have three segments in here. First of all, I have the whole segment AB. And then I also have, ooh, hot pink. So you probably can't see that in the video, I shouldn't use it. So that hot pink segment is AF. Hot AF. And then this, oh, where'd you go? Sorry, and then this last one is FB. Normally put lines on them, but that'll be a little bit more confusing for the notation, so they should be finite line segments. But this segment AB and this segment AF and this segment FB now, the golden cut is such that AB over the big segment FB is exactly equal to the big segment FB over AF, hot AF. So what does that mean? Instead of using geometric notation, what I'm going to do now is get rid of that magic. Where are you going? So now what we're going to do is, instead of using the geometric notation of all the points and giving you this horrible definition, what we want is, I'm going to call this segment X from here to here. And then we're going to call this actually the unit length. Whatever our unit length is, that is a unit length. And so what we can do in this cut is such that the ratio of the whole segment, which is now X plus 1, this segment, divided by or in ratio to the large segment X, has to be exactly the same as the large segment X over the shorter segment, which we call unity. Now that I have X's in there, what we're going to do is solve, and we're going to get quadratic, and then we use the quadratic formula to complete the square and find the two solutions. The positive solution to this quadratic formula is, in fact, the golden ratio, which we call phi, or the extreme and mean ratio. So let's do that. First of all, he has to go this way. Once I have it over here, now what I can do with that is cross multiply, and I'm going to get x plus 1 equals x squared. So I'm bringing this up to the other side, multiply both sides by x. I'm assuming it's not 0 because this is the length of part of that segment. Now I have a quadratic. The strategy is bring everything to one side. X squared minus x minus 1 equals 0. Good. And now I have a quadratic equation. Let's complete the square and solve for x. How do I do that? I don't need our starting equation. From that starting definition of the extreme and mean ratio, cutting it in a segment such that the large segment over the bigger segment, or the entire segment over the larger one, that ratio is equal to the large segment over the smaller one. Words, and what was that I said? X plus 1 over x has to equal x over 1. From that, we get a quadratic equation. From this now, I can solve for x. How do I do that? I complete the square. B is negative 1 over 2 is negative 1/2. B over 2 squared is negative 1/2 squared, which is, using exponent laws, is 1/4. That's the thing I need, but I can't just add that in, so I'm going to add 1/4 minus 1/4, which is 0. This now becomes x squared minus x plus 1/4, the thing I needed, but minus 1/4 minus 1 equals 0. I've added 0 right in the middle there. Why am I doing this? I'm now doing all these clever tricks to work at finding an exact expression for the golden ratio, something I want. So once I have this, this is now the completed square. So that is x minus b over 2 squared minus, now I need a common denominator. I'll multiply by my favorite dirty trick, 4 over 4, which is 1. So I get 5 over 4 equals 0. This is the completed square. Now I'm going to solve for x. How do I do that? First of all, bring this to the other side. So I have x minus 1/2 squared equals 5 over 4. Now I have to take the square root, remember, plus or minus. This gives me x minus 1/2 is equal to plus or minus the square root of 5 over the square root of 4. I used an exponent law there, or radical laws, they're the same thing. From this, I solve for x one more move. And we get x is equal to 1/2 plus or minus the square root of 5 over the square root of 4 is 2. This says x is equal to 1 plus the square root of 5 over 2, or x is equal to 1 minus the square root of 5 over 2. The golden ratio, phi, is this positive root, which is approximately equal to 1.618. We'll show you how to do that in another video that's coming soon. But this is the golden ratio. The definition again is I take any segment, I cut it in such a way that this ratio, the whole segment over the large segment, is equal to the large segment ratio over the smaller segment. Now I realize I was also silly, and I erased my original picture with my dots that I cooked up, so you can see how I cooked that up. First of all, get rid of this magic. So now I have to recook this up. What I'm going to do is I'm going to make 3 points. I know what the value is, so I'm cheating. I'm not actually geometrically constructing. I'm just being lazy. Here's how I lazily constructed the points I want. That'll be a 1, and then I need 0.6 roughly, because it's 1.6. So I need 2/3 of that roughly. So right there is roughly the golden cut. From that, we can make a square of that length, so then I'm going to have to do it up this way. Let's do it anyways. There's that one, and then I need 2/3 of this one roughly, which is about there. So we're now going to erect a perpendicular here. We're going to make a square from that. So then I can draw from the golden ratio. We can create the golden rectangle. Now you can see obviously I have a rectangle. Actually, I'm going to cheat because I have the tattoo right here. So using this golden rectangle, or using my width, I mean. I'm just going to figure everything out. And if I make a square of that length now, this now is another golden rectangle. So what that does nicely in art and in paintings, we have now a vanishing line to infinity, but in every one of these we have the same ratio in these rectangles. So as we go, we have a vanishing point, or a vanishing line, and a vanishing point, which is perspective preserving as we go out. So this is extremely useful in art as well. So if I do that again, I've made a square using this side. Now if I do that again, I can make a square over here. I get another golden rectangle. I'm going to do it again. I'm going to cheat this one now. I create right there roughly. I create the square. Then I'll cheat again. We're going to make roughly a square there. Then we're going to cheat again, and it's just going to keep going. And so now what we're going to do with that is, should we use, we'll use orange. For as close as I had to gold, I don't have a yellow. So now I connect those outside points. So starting somewhere, it converges to some point in there, but then we're going to connect this point, and then, oh, I cheated again. Then I can use that point, and then I use the outside points here, and then this point here, and then this point here, and this point here, and we will get the golden spiral from, and then it will come out there somewhere. We get the golden spiral. Maybe I can use a different color too now. And we can use hot pink. Hot pink. Use all the colors. Oh, hot pink ruined it. Hot pink ruined it. You're out of here. Straight out hot pink. I tried. So this is the golden ratio.